Welcome to part one of my series introducing quantum computing. I'm going to explain the origins and how it works. Quantum mechanics has some really strange consequences. One of them is quantum superposition, which is summarized in the famous thought experiment Schrödinger's cat. The idea is that if you have a cat inside a box described by quantum mechanics, this cat can be in a quantum superposition of being alive and dead at the same time. And this is an extreme example of the general phenomenon in quantum mechanics where a system described by quantum mechanics can be in multiple states at once. Another interesting aspect of quantum mechanics is quantum entanglement. If you take two systems, let them interact, then they can become quantum entangled. This means that they're correlated much more strongly than a classical system can be correlated. For example, a pair of socks that are the same color have a correlation, but entangled quantum systems are much more correlated than what is allowed classically. These phenomena of superposition and entanglement will come up a lot when we're talking about quantum computing and how it works. Let's talk about where the idea for quantum computing came from after the theory of quantum mechanics was developed. There are two main origin stories for quantum computing. One of them is from Richard Feynman, who made the point that if you think of chemical systems, they're actually described by quantum mechanics. So if you want to derive the properties of the periodic table, you better know quantum mechanics. And he reasoned that when we're trying to simulate the properties of chemicals that are actually described by quantum mechanics, the best hardware for simulating them would actually be quantum systems themselves. Quantum systems should lend themselves naturally to simulating the properties of quantum systems. So that's one origin of where the idea behind quantum computing came from. Another is from the physicist David Deutsch. Deutsch was imagining a thought experiment to try and test interpretations of quantum mechanics to show that they are actually experimentally different theories. The Schrödinger's cat thought experiment that I mentioned leads to this consequence of the cat seemingly being alive and dead at the same time. And there's controversy about whether a large macroscopic system like a cat can really be in quantum superposition, or if at some scale, maybe observing a cat or the cat observing the radioactive atom that it's inside this box with somehow causes the quantum system to collapse irreversibly into just a single state. There's these two different interpretations of quantum mechanics. One that says that an observation causes an irreversible collapse into a single state, and macroscopic systems can't be in these superpositions because they'll collapse into single states. And another theory that says that there is no collapse, there's no strange observer that causes a system to irreversibly collapse. Actually, when you measure a system, when the cat measures the radioactive atom, when you measure the cat, you become entangled. And so one version of you sees the cat dead, one version of you sees the cat alive. And this is the many worlds theory of quantum mechanics because it leads to an emergent conclusion that you have two versions of you, so multiple worlds. And by imagining how to test between these two theories, irreversible collapse and many worlds theory, Deutsch came up with an idea that essentially you'd need a quantum computer in order to do the experiment that he had in mind. And so that was a precursor to quantum computing as we know it today as well. So that's where some of the ideas of quantum computing came from. But now I want to introduce the actual building blocks that we're going to use to talk about quantum computing. Classical computers are based on bits. These can be 0 or 1. They can be in two different states, so we can flip between those states. Quantum computers are instead based on quantum bits called qubits, which map perfectly onto the surface of a sphere. The top of the sphere is the 0 state, the bottom is the 1, and every other point is a superposition of 0 and 1. And if your qubit is in a superposition of 0 and 1 and you measure it, then it will get projected into either the 0 state or the 1 state. So it'll only give you one of those two outcomes. You can imagine it using a coin analogy. The 0 is the heads, the 1 is the tails. In classical bits, you can flip between 0 and 1. With quantum bits, you can imagine the superposition being like a spinning coin, spinning through heads and tails. Now, it turns out that every single point on the sphere is a unique quantum state, a unique quantum superposition. If this state is closer to 0, then when you measure it, it has a higher probability of collapsing to the 0 state. If it's closer to 1, it has a higher probability of being projected into the 1 state and giving you the outcome of 1. Now, with classical bits, you can flip them 0 to 1, 1 to 0. With quantum bits, you can rotate around the different points on this sphere by applying a quantum gate. Let's look at some examples of common quantum gates that you'll find in quantum computing that are used to implement operations. One of them is the same one that you'll find in classical bits. So in the same way that you can flip your bits from 0 to 1, 1 to 0, you can flip your qubit from 0 to 1 and 1 to 0 by applying an X gate. There's another gate called the Hadamard gate, which puts you into a superposition. So this is uniquely quantum. And what the Hadamard gate does is if you're in the 0 state, it rotates you over to being 0 plus 1. And if you're in 0 plus 1, so superposition, it rotates you back to being in a fixed 0 state. So it can create a superposition. Finally, another important one is called the controlled NOT gate. And what this does, which is really cool, is that when we combine it with the Hadamard gate, we can actually create quantum entanglement between qubits. It acts on two qubits. It's controlled on the first qubit, and depending on what the state of the first qubit is, it will apply an X gate to the second qubit. So what we do is we prepare the first one with a Hadamard gate into a superposition of 0 and 1. And then, if the first one is 0, the controlled X does nothing to the second qubit. But if the first qubit is 1, then the controlled X applies an X gate to the second qubit so that it flips from 0 to 1. What we end up with after doing that is that the first qubit is 0 and the second qubit is 0 in one part of the state, and that's in superposition with both qubits being 1. And this notation here for describing the state is called Brouquet notation or Dirac notation. For this video, you don't need to have a detailed understanding of what that means. What it's really representing is vectors if you want to look into the mathematics of it, but it's a useful way of representing the quantum states. So you can see that we have a superposition of both qubits being 0. The plus means that we're putting them into superposition. And then we have the two qubits being 1. And this is this maximally entangled state called a Bell state. So this is how we can use these quantum gates to create these phenomena that we talked about at the beginning. We can see how it can create entanglement here and create superposition here with the Hadamard gate. So those are the basic quantum gates. Now, the next step that got people's attention with quantum computing, beyond being a kind of interesting concept to do computing based on these qubits was the Deutsch-Jozsa algorithm. So this is the first algorithm which showed that you can actually find the outcome of a computation with fewer steps with a quantum computer than with a classical one. It's a question about this mathematical function of x. The question is whether it has the property of being constant or balanced. So it's just a question of which of these two properties does this function have. Using a classical computer, answering this question would require 2 steps. You'd have to run it twice. But with a quantum computer, you can just run this function once and get the answer. This was the first example showing that there's a certain task. We're asking this question of what's the property of this function, and you could find out the answer to your question in fewer steps with a quantum computer than with a classical one. But what really got the attention of a broader community into quantum computing is when Shor's algorithm came along. Shor's algorithm was the first algorithm which showed a really potentially large quantum speedup for a really useful mathematical problem. And it's also one that created a threat which people are still thinking a lot about today. The idea of Shor's algorithm is to do with the mathematical problem of factorization. If you have 2 prime numbers and you multiply them, that can be done efficiently on a classical computer. But factorizing a large number into its prime factors is notoriously difficult. And the fact that this is difficult on a classical computer is the basis for our crypto systems that are used in cybersecurity, RSA. And so those systems rely on the difficulty of this reverse process of factorization. But then Shor's algorithm came along, and Peter Shor showed that when you had access to a really good quantum computer, you could actually efficiently factorize a large number into its prime factors, breaking the basis of these protocols that are used in cybersecurity and are really widespread and have lots of secure systems relying on them. This really got people's attention because it's an important problem and also showed a vast speed up with quantum computers. And there's this question of, should we be worried about this algorithm? Is someone going to hack into all of our data with a quantum computer anytime soon, making use of this? And there's 2 answers to this. One of them is that we're still a long way off from having a quantum computer that could solve this kind of problem. It has to be a really good one to be able to do this. So in that sense, there's lots of time to prepare and to see it coming when there might be a quantum computer good enough to solve this kind of problem. On the other hand, there is the possibility of people harvesting data now in order to hack later when quantum computers are available in the future. And there's data today that might still be valuable whenever we have a quantum computer good enough to do this. So that's why there's a movement to try and shift to post-quantum cryptography. So that's cryptography that's safe against attacks from quantum computers. Although this shift comes with its own complexity, because often doing a switch to a post-quantum system has its own drawbacks, costs, and risks, because if it's not well tested enough, then maybe there's some way it can even be hacked with a classical computer that no one's come up with yet. So there's lots of interesting issues around figuring out the best way to deal with the security impacts of quantum computers becoming better and better in the future. So that's part 1 of my series Introducing Quantum Computing. Join me in the next episode for part 2, where I'll discuss the challenges of quantum computing.